Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. How asteroids can have their own moons. The first asteroid moon was discovered in 1993, when the Galileo spacecraft, on its way to Jupiter, flew past an asteroid named Ida and transmitted images showing a small companion orbiting it. The discovery surprised many scientists. Ida itself is only about 56 kilometers long, an irregular, potato-shaped chunk of rock tumbling through space. Its tiny moon, later named Dactyl, measures merely 1.4 kilometers across. How could such a small object, with such weak gravity, possibly hold onto a moon? This discovery opened an entirely new chapter in our understanding of asteroids, revealing that these ancient fragments of the early solar system are far more complex and dynamic than anyone had imagined. The key to understanding asteroid moons lies in recognizing that gravity, no matter how weak, still operates according to the same laws, whether you're considering a massive planet or a tiny asteroid. Every object with mass generates a gravitational field, and that field extends infinitely into space, weakening with distance, but never disappearing entirely. An asteroid's gravity is incredibly feeble compared to a planet's. Ida's surface gravity is only about 0.3 to 1% of Earth's, depending on where you measure it, on the irregular surface. But this tiny gravitational pull is sufficient to influence nearby objects, and under the right circumstances, it can capture and hold a moon in orbit. The mechanics of orbital motion around an asteroid differ significantly from orbits around planets. Planets are generally spherical, or nearly so, which means their gravitational fields are relatively simple. They approximate the field of a point mass located at the planet's center. Asteroids, however, are often highly irregular, shaped like elongated potatoes, peanuts, or even contact binaries where two lobes are stuck together. This irregular shape creates a complex gravitational field with multiple peaks and valleys, regions where the gravitational pull is stronger or weaker than average. An object orbiting an irregular asteroid doesn't follow a simple ellipse the way a planet orbits the Sun. The orbit wobbles and shifts due to the uneven gravity field. Additionally, most asteroids rotate, and this rotation causes the gravitational field to change over time from the perspective of an orbiting object. The combination of irregular shape and rotation creates a challenging environment for stable orbits. Yet despite these complications, asteroid moons not only exist but are surprisingly common. Current estimates suggest that about 15% of near-Earth asteroids have companions, and the fraction is even higher among certain populations. Asteroid moons form through several mechanisms, each revealing something about the dynamic processes that shape these small bodies. The first mechanism is capture. Similar to how planets can capture moons, though the process works differently at asteroid scales. When two asteroids pass close to each other, they normally just fly past, perhaps exchanging some momentum through gravitational interaction, but remaining on separate trajectories. However, if a third body is nearby during the encounter, it can absorb some of the kinetic energy through a three-body gravitational interaction, allowing one asteroid to be captured into orbit around the other. This three-body capture was more common in the early solar system, when asteroids were more numerous and encounters more frequent. The asteroid belt, located between Mars and Jupiter, contains hundreds of thousands of asteroids larger than 1 kilometer and millions of smaller ones. In the denser environment of the early solar system, close encounters between 3 or more asteroids occurred regularly, providing opportunities for capture. Once captured, the orbit would gradually stabilize through tidal interactions and additional gravitational perturbations. Collisions represent another pathway to moon formation. The asteroid belt is a violent place where collisions occur regularly on geological timescales. When two asteroids collide, the impact doesn't necessarily destroy both objects. Depending on the impact velocity and angle, a collision might excavate a crater and eject material into space. Some of this ejected material falls back onto the asteroid, but some of it enters orbit around the shattered parent body. Over time, these orbiting fragments can collide with each other and coalesce into a moon. The collision scenario explains why many asteroid moons orbit very close to their parents and have compositions similar to the parent asteroid. If a moon formed from impact debris, it would naturally be made of the same material as the parent. Studies of asteroid pairs, asteroids with very similar orbits and compositions, suggest that many originated as fragments from catastrophic collisions that split a parent asteroid into two or more large pieces. In some cases, these pieces remain gravitationally bound, creating a binary asteroid system. The YORP effect provides a third mechanism for creating asteroid moons, and it's one of the most fascinating processes in asteroid dynamics. YORP stands for Yarkovsky-O'Keefe-Radzievsky-Paddock, named after the scientists who contributed to understanding this phenomenon. The YORP effect occurs when sunlight reflecting off an asteroid's irregular surface creates tiny torques that gradually change the asteroid's rotation rate. The effect is incredibly small. It might change an asteroid's rotation period by only milliseconds per year, but over millions of years, these tiny changes accumulate. As the YORP effect spins an asteroid faster and faster, centrifugal forces at the equator increase. Eventually, the asteroid might be rotating so fast that material at the equator experiences outward centrifugal forces that exceed the inward gravitational forces. At this point, material begins to lift off the surface and enter orbit, forming a ring or disk around the asteroid. This orbiting material can then aggregate into one or more moonlets. Computer simulations and observations of very rapidly rotating asteroids support this mechanism. Asteroid 1999 KW4 provides a clear example of the YORP effect in action. This binary asteroid system consists of a larger primary asteroid, about 1.3 kilometers in diameter, rotating once every 2.8 hours, extremely fast for an object this size. A smaller satellite, about 360 meters across, orbits the primary at a distance of about 2.6 kilometers. The primary asteroid has a distinct equatorial ridge, exactly what would be expected if centrifugal forces had been pushing material toward the equator. The satellite likely formed from material that was flung off this equatorial region when the primary was spinning even faster in the past. The rotation rates of asteroids play a crucial role in their ability to hold moons. There's a limiting rotation rate, typically around one rotation every 2 to 3 hours for a solid asteroid, beyond which centrifugal forces would tear the asteroid apart. This limit, called the critical spin limit, depends on the asteroid's size, shape, and material strength. Asteroids can spin faster than this limit only if they're held together by internal strength, essentially solid rocks, rather than just gravity. Many asteroids appear to be rubble piles, loose aggregations of boulders and gravel, held together primarily by their own weak gravity, with little internal strength. These rubble pile asteroids cannot spin faster than the critical limit without shedding material or breaking apart. The Roche limit becomes relevant for asteroid moons, just as it does for planetary moons. The Roche limit is the distance inside which tidal forces would tear apart a satellite that's held together only by its own gravity. For solid objects held together by material strength, they can orbit inside the Roche limit without being destroyed, though they experience severe tidal stresses. Many asteroid moons orbit near or even slightly inside the classical Roche limit for a fluid body, suggesting that they're solid objects with sufficient strength to resist tidal disruption. Binary asteroids, where two similarly sized objects orbit their common center of mass, represent a special category. In these systems, neither object is clearly the moon of the other. They're more like double asteroids, co-orbiting companions. The Pluto-Charon system is arguably a binary system, though Pluto is now classified as a dwarf planet rather than an asteroid. Among smaller asteroids, binary systems are not uncommon. The asteroid Antiope consists of two objects, each about 88 kilometers in diameter, orbiting their common center of mass at a separation of about 170 kilometers. These binary systems likely form from gentle collisions or from the splitting of a rapidly rotating parent body. When an asteroid spins fast enough, it can develop a dumbbell or peanut shape, elongated along its equatorial plane. If the spin increases further, the dumbbell can split at its narrow center, creating two separate bodies. Because they formed from the same parent, they initially have very similar velocities and remain gravitationally bound, orbiting each other. Observing asteroid moons requires careful astronomical work. Most asteroids are too small and distant to be resolved as disks even through powerful telescopes. They appear as points of light. Their moons are even fainter and closer to the primary, making direct imaging challenging. However, several techniques reveal their presence. Light curve analysis measures how an asteroid's brightness changes over time as it rotates. A simple asteroid produces a regular, repeating pattern, but if a moon is present, it creates additional dips or bumps in the light curve as it passes in front of or behind the primary asteroid, or as it reflects additional light toward Earth. Radar observations provide another powerful technique. When radio waves are bounced off an asteroid, the reflected signal contains information about the asteroid's shape, rotation, and surface features. If a moon is present, it appears as a separate echo in the radar data, delayed relative to the primary's echo by the light travel time to the more distant moon. The Arecibo Observatory in Puerto Rico and the Goldstone Solar System Radar in California have discovered dozens of asteroid moons through radar observations of near-Earth asteroids as they pass relatively close to Earth. Spacecraft missions provide the most detailed views of asteroid moons. After Galileo's discovery of Dactyl orbiting Ida, subsequent missions have encountered other asteroid systems. The Near-Shoemaker spacecraft orbited asteroid Eros, which has no moon, but provided detailed information about asteroid composition and structure that helped interpret observations of binary systems. The Dawn mission visited the large asteroids Vesta and Ceres, also moonless, but revealed the complex geology of these protoplanets. Future missions specifically targeting binary asteroids will provide unprecedented insights into these systems. The existence of asteroid moons has practical implications beyond pure science. Some near-Earth asteroids pose potential collision hazards to Earth, and understanding whether they have moons affects how we might deflect them if necessary. A binary asteroid system behaves differently than a single asteroid when subjected to external forces. The NASA DART mission, launched in 2021, deliberately crashed a spacecraft into Dimorphos, the moon of the asteroid Didymos, to test whether kinetic impacts could alter an asteroid's orbit, a potential planetary defense technique. The mission successfully changed Dimorphos's orbital period, demonstrating that asteroid moons respond to impacts in measurable ways. The orbital dynamics of asteroid moon systems are surprisingly rich because the gravitational fields are so weak. Other forces become relatively more important. Solar radiation pressure, the physical push exerted by sunlight, can perturb asteroid moon orbits significantly over time. The orbits slowly evolve, sometimes becoming more circular, sometimes more elliptical, depending on the specific configuration. Tidal forces between the asteroid and its moon, though tiny, gradually exchange angular momentum, causing the Moon to migrate inward or outward over millions of years, potentially leading to eventual escape or collision. Triple asteroid systems exist as well, where one asteroid has two moons, or where three similarly sized bodies orbit their common centre of mass. The asteroid Sylvia, about 260 kilometres in diameter, has two known moons named Romulus and Remus, discovered in 2001 and 2004 respectively. Romulus orbits at about 1,360 kilometres from Sylvia, with an orbital period of 3.6 days. Remus orbits closer, at about 710 kilometres, with a period of 1.4 days. These multiple moon systems provide natural laboratories for studying gravitational dynamics in the weak field limit. The study of asteroid moons illuminates the processes that operated during planet formation. Planets grew through collisions and mergers of smaller bodies, asteroids, and planetesimals. Understanding how these small bodies interact, collide, capture each other, and form bound systems helps us understand the early stages of planet formation. Every asteroid moon is a relic of these ancient processes, a small-scale version of the interactions that built planets from swarms of orbiting debris billions of years ago. The discovery that asteroids can have moons transformed them from simple rocks floating in space into complex, evolving systems with their own orbital dynamics, formation histories, and future fates. These tiny moons orbiting tiny worlds demonstrate that the fundamental laws of gravity and motion operate at all scales, creating structure and dynamics from the largest galaxy clusters down to kilometre-sized rocks tumbling through the asteroid belt. Each small moon a reminder that even the weakest gravity can bind objects together across the emptiness of space. How aliens could breathe different atmospheres. When we imagine aliens visiting Earth in science fiction, they often step out of their spacecraft and breathe our air without difficulty, or they wear helmets and breathing apparatus because our atmosphere is toxic to them. Both scenarios recognize a fundamental truth. The atmosphere that sustains one form of life might be useless or deadly to another. On Earth, oxygen is essential for most complex life, powering the high-energy metabolisms of animals through cellular respiration. But oxygen wasn't always abundant in Earth's atmosphere, and even today, many organisms live without it, thriving in environments where oxygen is scarce or absent. Understanding how aliens could breathe different atmospheres means understanding the relationship between atmospheric gases and metabolism, the chemistry of energy extraction, and the remarkable adaptability that evolution can produce when organisms face different atmospheric conditions. Earth's atmosphere is about 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, water vapour, and other gases. This composition seems normal because it's all we've known, but it's actually quite unusual from a cosmic perspective. Oxygen is highly reactive. It combines readily with many elements, forming oxides that are stable and chemically inert. Free oxygen shouldn't persist in a planet's atmosphere for long unless something continually replenishes it. On Earth, that something is photosynthetic life. Plants, algae, and photosynthetic bacteria capture sunlight and use its energy to split water molecules, releasing oxygen as a byproduct. Without life constantly producing oxygen, Earth's atmosphere would gradually lose its oxygen as the gas reacted with rocks, metals, and organic molecules, eventually leaving an atmosphere dominated by nitrogen and carbon dioxide. For the first 2 billion years, or more of Earth's history, the atmosphere contained very little free oxygen. Early life evolved in this oxygen-poor world, using different metabolic pathways that didn't require oxygen. Even today, many organisms live in oxygen-free environments, deep in ocean sediments, in the intestines of animals, in waterlogged soils, where oxygen cannot penetrate. These anaerobic organisms use alternative molecules as the final electron acceptors in their metabolism. Some use sulfur compounds, reducing sulfate to hydrogen sulfide, the gas that smells like rotten eggs. Others use nitrates, producing nitrogen gas. Still others use carbon dioxide itself, producing methane. These metabolisms are less efficient than oxygen-based metabolism, releasing less energy per molecule of food consumed, but they work well enough to sustain life. An alien planet that never developed photosynthetic life might retain an oxygen-poor atmosphere indefinitely. Life on such a world would necessarily use anaerobic metabolism, breathing gases we would consider unusual or toxic. Hydrogen sulfide, lethal to most Earth animals, could serve as the oxidizing agent in alien metabolism. Organisms might inhale hydrogen sulfide and exhale elemental sulfur or some other sulfur compound. Their biochemistry would be built around sulfur chemistry, the way ours is built around oxygen chemistry. These aliens would find Earth's oxygen-rich atmosphere as toxic as we find hydrogen sulfide. Oxygen would react with their sulfur-based biochemistry, disrupting the carefully balanced chemical reactions that keep them alive. Methane represents another possibility. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms, and it exists as a gas at temperatures where water is liquid. Some Earth organisms produce methane as a waste product of their metabolism, and these methane-producing microbes, called methanogens, thrive in oxygen-free environments, like swamps, rice paddies, and the digestive systems of cattle. Methane is flammable in the presence of oxygen, but in an oxygen-free atmosphere, it's stable. A planet with abundant methane in its atmosphere might support life that uses methane in its metabolism, perhaps breaking down methane to extract energy or using methane as a raw material to build more complex organic molecules. Titan, Saturn's largest moon, has an atmosphere dense with nitrogen and methane, with no free oxygen. The surface temperature hovers around -180 degrees Celsius, cold enough that water is frozen as hard as rock, while methane exists as liquid in lakes and seas. If life exists on Titan, a big if, but not impossible, it would necessarily be adapted to breathe this nitrogen-methane atmosphere and might even metabolize in ways that involve liquid methane rather than liquid water. Such organisms would be completely incompatible with Earth's environment. Bringing them to Earth would be like throwing a fish into a furnace. The heat alone would destroy them before oxygen toxicity became an issue. Carbon dioxide-rich atmospheres present another scenario. Venus has an atmosphere that's about 96% carbon dioxide, creating a crushing surface pressure about 90 times Earth's atmospheric pressure, and a runaway greenhouse effect that raises surface temperatures to over 450 degrees Celsius. No life could exist in Venus's current conditions, but a cooler planet with a carbon dioxide atmosphere and might be habitable. Some Earth organisms already tolerate high carbon dioxide levels that would kill humans. Deep-sea hydrothermal vent communities, for instance, experience high carbon dioxide concentrations dissolved in water. Organisms adapted to such environments have specialized biochemistry that allows them to function despite the high carbon dioxide. Aliens from a carbon dioxide-rich world might metabolize in ways that involve carbon dioxide directly. Perhaps they would use carbon dioxide as an oxidizing agent, combining it with hydrogen-rich compounds to extract energy, producing methane or other hydrocarbons as waste products. Or they might use carbon dioxide as a raw material, building organic molecules from carbon dioxide the way plants do, but doing so as part of their metabolic processes rather than as a separate photosynthetic function. These aliens might find oxygen toxic and carbon dioxide essential, the opposite of most Earth animals. Ammonia is another gas that could potentially play a role in alien respiration. Ammonia is toxic to most Earth life, disrupting pH balance and interfering with normal biochemistry. But at lower temperatures, ammonia can exist as a liquid, and some scientists have speculated that ammonia could serve as a solvent for biochemistry on very cold worlds, potentially replacing water. An atmosphere with significant ammonia might support organisms that breathe ammonia, using it in their metabolism in ways we can barely imagine. The chemistry would be entirely different from oxygen-based metabolism, operating through different pathways and producing different waste products. Chlorine and fluorine, both highly reactive halogens, represent more exotic possibilities. These gases are extremely reactive and toxic to Earth life, but that's precisely because they're good at accepting electrons, the same property that makes oxygen useful for metabolism. An organism that evolved in an atmosphere containing chlorine or fluorine might use these gases the way we use oxygen, combining them with food molecules to extract energy. The waste products would be chlorides or fluorides rather than the water and carbon dioxide that Earth animals produce. Such organisms would find Earth's atmosphere lacking. Our oxygen, while reactive, wouldn't fit into their chlorine-based or fluorine-based biochemistry. They would suffocate in our air despite it containing a highly reactive gas. The partial pressure of gases matters as much as their chemical identity. Partial pressure is the pressure contributed by a specific gas in a mixture. For instance, Earth's atmosphere has a total pressure at sea level of about 1 atmosphere, and oxygen makes up 21% of that. So oxygen's partial pressure is about 0.21 atmospheres. Humans need oxygen at roughly this partial pressure to survive. Too little at high altitudes where atmospheric pressure drops and we suffer hypoxia, unable to get enough oxygen into our blood. Too much in pure oxygen at high pressure, and oxygen becomes toxic, causing seizures and lung damage. Aliens would have similar constraints based on their biochemistry. An alien that breathes hydrogen sulfide might need it at a specific partial pressure. Too little, and their metabolism cannot function efficiently. Too much, and it becomes toxic even to them. This means that even if two species breathe the same gas, they might not be able to share the same atmosphere if they require different partial pressures. An alien adapted to breathe oxygen at very low partial pressures, perhaps from a high-altitude environment or a planet with thin atmosphere, might suffocate in Earth's oxygen-rich air, not from lack of oxygen, but from oxygen toxicity. Temperature affects which molecules can exist as gases. On Earth, at our range of temperatures, nitrogen, oxygen, carbon dioxide, and water vapor exist as gases, while water also exists as liquid. On a much hotter planet, perhaps one close to its star, gases we don't encounter might be common. Sulfur compounds that are liquids or solids on Earth might be gases on a hot world. Metals like mercury or even iron could exist as vapor in the atmosphere of an extremely hot planet. Life on such a world, if it could exist at all, might breathe exotic gases that would condense into liquids or solids in Earth's relatively cool atmosphere. Conversely, on extremely cold worlds, gases that are common on Earth might be frozen solid. On Pluto, where temperatures drop to around -230 degrees Celsius, nitrogen, which makes up most of Earth's atmosphere, freezes into solid nitrogen ice. Pluto's thin atmosphere consists of nitrogen, methane, and carbon monoxide that sublimates from surface ices when Pluto is closest to the Sun in its elliptical orbit, then freeze back out when Pluto moves farther away. Life on such a cold world would need to breathe gases that remain gaseous at these extreme temperatures, or it would need to exist in warmer subsurface environments where different conditions prevail. The evolution of breathing mechanisms would differ based on atmospheric composition and pressure. On Earth, animals evolved lungs, gills, tracheal systems, and other specialized structures to extract oxygen from air or water. Fish gills expose blood to water flowing past thin membranes, allowing oxygen to diffuse from water into blood. Insect tracheal systems deliver air directly to cells through branching tubes. Mammalian lungs use millions of tiny air sacs to maximize surface area for gas exchange. Each system is optimized for extracting oxygen from Earth's atmosphere or water. Aliens breathing different atmospheres would evolve different respiratory structures optimized for their specific gases. An alien breathing a very dense atmosphere, perhaps with pressures many times Earth's, might have very small respiratory surfaces because gases would diffuse quickly at high pressure. An alien breathing a thin atmosphere might need enormous respiratory organs to capture enough of their necessary gas. An alien breathing a gas that dissolves poorly in their body, fluids might need respiratory pigments, molecules like hemoglobin in our blood, specifically designed to bind and transport their particular gas. Some aliens might not breathe at all in the sense of moving gases in and out of their bodies. Single-celled organisms on Earth absorb oxygen directly through their cell membranes without any respiratory system. An alien with a radically different body plan, perhaps resembling Earth's sponges or fungi more than animals, might absorb needed gases through its entire surface area, rather than through specialized breathing organs. Or an alien might rely entirely on anaerobic metabolism happening within its cells, never needing to extract gases from the environment at all, living on chemical energy stored in molecules absorbed from its surroundings. The possibility of breathing different atmospheres means that habitable zones around stars become more complex. The traditional habitable zone focuses on temperature, the range where liquid water can exist. But a habitability zone could be defined for any solvent and any metabolic gas. There's a methane habitability zone at different temperatures where methane is liquid. There's a hydrogen sulfide habitability zone where that gas exists at suitable pressures. There's an ammonia habitability zone at very cold temperatures. Each zone would support fundamentally different kinds of life adapted to its specific conditions. If humans ever encounter aliens, the atmospheric incompatibility would be one of the first obvious differences. We couldn't share environments without life support equipment. An alien from an ammonia world would need refrigeration and ammonia supplies to survive in Earth's environment. We would need oxygen supplies and temperature regulation to survive in theirs. Even communication would be affected. Sound travels differently in different atmospheric gases. In a dense carbon dioxide atmosphere, sound would be lower pitched and quieter. In a thin hydrogen atmosphere, sound would be higher pitched and travel faster. An alien's voice might be physically impossible for human ears to hear without electronic translation. How aliens could breathe different atmospheres ultimately reflects the diversity of chemistry and the flexibility of evolution. Life adapts to available conditions, and the chemistry that powers metabolism is not limited to oxygen and carbon dioxide. From hydrogen sulfide to methane, from ammonia to chlorine, from thin atmospheres to crushing pressures, from scorching heat to numbing cold, life, if it exists elsewhere, would develop respiratory systems suited to its world's specific conditions, breathing atmospheres that might kill us in seconds, while finding our oxygen-rich air as toxic and alien as we would find theirs, proving that the breath of life can take as many forms as there are worlds scattered across the universe. How black holes warp time itself. Time is not the constant, uniform flow that our everyday experience suggests. It can stretch, compress, and slow down, depending on the gravitational environment you're in. Nowhere is this more extreme than near a black hole, where gravity becomes so intense that time itself warps, in ways that challenge our intuition and transform our understanding of reality. Understanding how black holes affect time means grappling with one of the most profound insights of modern physics, that space and time are not separate, fixed stages on which events unfold, but rather a unified fabric that can be bent, twisted, and stretched by the presence of mass and energy. The foundation for understanding time dilation near black holes comes from Albert Einstein's general theory of relativity, published in 1915. Einstein proposed that what we perceive as gravity is actually the curvature of space-time caused by mass and energy. Massive objects create depressions in the fabric of space-time. Much like a bowling ball placed on a stretched rubber sheet creates a depression that affects how nearby marbles roll. This curvature affects not just the paths that objects follow through space, but also the rate at which time passes. The basic principle is that time passes more slowly in stronger gravitational fields. This effect, called gravitational time dilation, has been confirmed through countless experiments. Atomic clocks placed at different altitudes on Earth tick at measurably different rates. Clocks at sea level run slightly slower than clocks on mountaintops, because they're deeper in Earth's gravitational well. The difference is tiny, only nanoseconds per day, but it's real and measurable. GPS satellites must account for this effect. Without corrections for gravitational time dilation, GPS coordinates would drift by several kilometers per day. Near a black hole, gravitational time dilation becomes extreme. Imagine two observers, one hovering far from a black hole in weak gravity, the other hovering closer to the black hole, where gravity is much stronger. If both observers synchronize their watches and then separate, the watch closer to the black hole will tick more slowly from the distant observer's perspective. This isn't an illusion or a malfunction of the watch. Time genuinely passes more slowly in the stronger gravitational field. The closer you get to a black hole, the more severe this effect becomes. At the event horizon, the boundary beyond which nothing can escape, time dilation becomes infinite from the perspective of a distant observer. This creates one of the most counterintuitive aspects of black holes. If you were to watch someone fall toward a black hole while you remained safely far away, you would see something strange. As the falling person approached the event horizon, they would appear to slow down. Their movements would become sluggish, their signals would take longer to reach you, and their image would become increasingly red-shifted as the light they emit is stretched by the intense gravity. From your distant vantage point, the falling person would never quite seem to cross the event horizon. They would appear to freeze at the boundary, becoming dimmer and redder until they faded from view entirely. This isn't because they stopped falling. From their own perspective, they would cross the event horizon and continue falling inward in a finite amount of time, experiencing nothing unusual at that precise moment. The difference is entirely due to how time flows differently in different gravitational fields. This discrepancy between what the falling observer experiences and what the distant observer sees is one of the most mind-bending aspects of general relativity. Both perspectives are equally valid. The falling observer crosses the event horizon in, say, 10 seconds by their clock, but from the distant observer's perspective, watching that crossing would take infinite time. It would never be complete. This isn't a contradiction, but rather a demonstration that time is not absolute. Different observers in different gravitational fields experience time at different rates. The mathematics describing this time dilation near black holes was first worked out by Carl Schwarzschild in 1916, just months after Einstein published general relativity. Schwarzschild found an exact solution to Einstein's equations describing the spacetime around a non-rotating, spherically symmetric mass, what we now call a Schwarzschild black hole. His solution showed that time dilation increases as you approach the event horizon, located at what's now called the Schwarzschild radius, reaching infinite dilation exactly at the horizon. For a rotating black hole, described by the Kerr solution, found by Roy Kerr in 1963, the situation becomes even more complex. Rotation creates additional effects beyond simple time dilation. The black hole drags spacetime around with it in a process called frame dragging. Close to a rotating black hole, space itself is pulled around in the direction of rotation. You couldn't remain stationary even if you wanted to. You'd be forced to rotate with the spacetime itself. This creates regions like the ergosphere outside the event horizon, where frame dragging is so strong that everything must move in the direction of the black hole's rotation. The warping of time near black holes has practical implications for anything orbiting or falling toward them. Consider material in an accretion disk spiraling into a black hole. Material in the inner portions of the disk, closer to the black hole, experiences stronger time dilation than material farther out. From the perspective of an observer far from the black hole, processes in the inner disk appear to run in slow motion compared to processes in the outer disk. This affects how we observe black holes and interpret the light we receive from matter near them. Time dilation also affects the gravitational redshift of light, escaping from near a black hole. Light climbing out of a gravitational well loses energy, its wavelength stretching toward the red end of the spectrum. This gravitational redshift is intimately connected to time dilation. They're two aspects of the same phenomenon. A photon emitted from close to the event horizon will be dramatically redshifted by the time it reaches a distant observer. If the photon is emitted from the event horizon itself, it would be redshifted infinitely, its energy dropping to zero, another way of understanding why nothing can escape from beyond the horizon. Inside the event horizon, the warping of spacetime becomes even more extreme. In this region, the roles of space and time actually exchange in a sense. Outside the horizon, moving forward in time is inevitable. You cannot choose to move backward in time, but you can choose your direction in space. Inside the horizon, moving toward the singularity at the center becomes as inevitable as moving forward in time outside the horizon. All possible paths lead inward, and reaching the singularity becomes as unavoidable as reaching the next moment in time. The singularity at the center of a black hole represents a place where space-time curvature becomes infinite, and general relativity's equations break down. At the singularity, time itself becomes undefined in the classical sense. This suggests that general relativity is incomplete, that a theory of quantum gravity would be needed to properly describe what happens at and beyond the singularity. String theory, loop quantum gravity, and other approaches to quantum gravity propose different solutions to what occurs at this extreme limit, but none have been confirmed experimentally. Supermassive black holes at the centers of galaxies create fascinating time dilation effects on galactic scales. The black hole at the center of our Milky Way galaxy, called Sagittarius A star, contains about 4 million solar masses. Stars orbiting close to this black hole experience measurable time dilation. A star in a close orbit around Sagittarius A star, coming within a few hundred times the black hole's event horizon radius, would experience time flowing noticeably slower than we experience it here on Earth, 26,000 light-years away. Precise measurements of these stars' orbits by Andrea Ghez and Reinhard Genzel, who shared the 2020 Nobel Prize in Physics for this work, have confirmed general relativity's predictions in this strong gravity regime. Time dilation near black holes has captured popular imagination, featuring prominently in science fiction. The film Interstellar depicted a planet orbiting close to a massive rotating black hole, where time dilation was so extreme that 1 hour on the planet's surface equaled 7 years of time passing elsewhere. While Hollywood took some liberties, the basic physics was sound. Physicist Kip Thorne served as scientific consultant and later published papers about the black hole physics portrayed in the film. Such extreme time dilation is theoretically possible near a rapidly rotating supermassive black hole. Binary black hole systems, where two black holes orbit each other before merging, create incredibly complex space-time geometries. Each black hole warps time in its vicinity, and the combined warping creates regions where time flows at different rates depending on your location relative to the two black holes. As the black holes spiral together and merge, events that produce the gravitational waves detected by LIGO and other observatories, the warping of spacetime becomes dynamical, with gravitational waves carrying information about how spacetime is oscillating and rippling during this violent event. The connection between time dilation and energy offers another perspective on these phenomena. According to general relativity, gravitational fields contain energy. A clock deep in a gravitational well, where time runs slowly, can be thought of as having less energy than a clock far from any gravitational source. The gravitational redshift of light, the loss of energy as light climbs out of a gravitational well, reflects this energy difference between different regions of curved spacetime. Black holes also raise profound questions about the nature of time itself. Some interpretations of quantum mechanics and general relativity suggest that time might not be fundamental, but rather an emergent property of more basic physical processes. Black holes, where classical notions of time break down at the singularity, might provide clues about the true nature of time. The information paradox, the question of what happens to information that falls into a black hole, connects to deep questions about time, entropy, and the quantum nature of spacetime. Hawking radiation, predicted by Stephen Hawking in 1974, introduces another connection between black holes and time. Quantum effects near the event horizon cause black holes to emit radiation and slowly evaporate over extremely long timescales. This process involves virtual particle pairs appearing near the horizon, with one particle falling in while the other escapes. The evaporation means black holes have a finite lifetime, and it connects quantum mechanics, gravity, and thermodynamics in ways that hint at a deeper theory unifying these domains. The warping of time near black holes is not science fiction, but established physics, confirmed through observations and experiments. Every time LIGO detects gravitational waves from merging black holes, it's detecting ripples in spacetime that carry information about how dramatically spacetime, and therefore time itself, was warped during the merger. Every observation of matter orbiting near black holes, every measurement of gravitational redshift, every test of general relativity in strong gravitational fields, confirms that time is not absolute, but is woven into the fabric of spacetime, susceptible to warping and stretching by mass and energy, reaching its most extreme manifestation near black holes, where the flow of time slows to a crawl, and ultimately, at the event horizon, appears to stop entirely from the perspective of distant observers watching the inexorable pull of gravity on the fabric of reality itself. Why space is nearly empty? When you look up at the night sky, space appears crowded with stars, planets, and galaxies. Photographs from telescopes show spectacular images of colourful nebulae, dense star clusters, and brilliant galaxies packed with hundreds of billions of stars. These images create an impression of a cosmos teeming with matter, a universe filled to the brim with celestial objects. But this impression is profoundly misleading. Space is almost unimaginably empty. The distances between objects are so vast and the objects themselves so small relative to those distances that if you could somehow travel to a random location in the universe, the overwhelming likelihood is that you would find yourself surrounded by nothing. No stars, no planets, no gas, no dust, for distances stretching farther than you could travel in a lifetime, even at the speed of light. To understand just how empty space is, consider the space between Earth and the Moon. The Moon orbits at an average distance of about 380,000 kilometers from Earth. That's far enough that you could fit all the other planets in the solar system side by side in the gap between Earth and the Moon, with room to spare. Now imagine taking a sphere with a radius equal to this Earth-Moon distance. Within that enormous volume, there are only two objects of any significant size, Earth and the Moon themselves. Everything else is emptiness, with only occasional atoms of gas or tiny dust particles scattered throughout. The situation becomes even more extreme when you consider the space between planets. Earth orbits about 150 million kilometers from the Sun. Mars orbits about 230 million kilometers from the Sun. The distance between Earth and Mars varies as both planets orbit, but at their closest approach, they're separated by about 55 million kilometers. This vast gulf contains essentially nothing. No planets, no moons, just a scattering of asteroids so small and so far apart that even if you were travelling through this region, you would be extraordinarily unlikely to come anywhere near one. The asteroid belt, often depicted in science fiction as a dense field of tumbling rocks that spaceships must carefully navigate, is in reality astonishingly sparse. The belt contains hundreds of thousands of asteroids larger than 1 kilometer across and millions of smaller ones. This sounds like a lot, and by the standards of everyday experience it is. But these asteroids are spread across an enormous volume of space, a region extending from about 300 million kilometers to 500 million kilometers from the Sun, and spanning the full circumference around the Sun at these distances. The result is that the average distance between asteroids is measured in millions of kilometers. If you were to travel through the asteroid belt, you would see nothing for days or weeks of travel before coming near even a single asteroid. The density of matter in the asteroid belt averages far less than 1 particle per cubic kilometer. Compare this to air at sea level on Earth, which contains about 10 to the 25th particles per cubic kilometer, a 1 followed by 25 zeros. The asteroid belt, despite containing countless asteroids, is millions of billions of times less dense than the air you're breathing right now. Every spacecraft we've sent through the asteroid belt, and many have made the journey, has passed through without incident, without needing to dodge asteroids, simply because the belt is so incredibly empty. Beyond the planets, the emptiness becomes even more profound. The nearest star to our Sun, Proxima Centauri, lies about 40 trillion kilometers away, a distance so vast that light, travelling at 300,000 kilometers per second, takes over 4 years to cross it. If you scaled the Sun down to the size of a basketball, Earth would be a grain of sand orbiting about 25 meters away, and Proxima Centauri would be another basketball more than 6,000 kilometers away. The sphere of space between these two basketballs contains essentially nothing. No planets, no asteroids, no comets that we know of, just occasional atoms of hydrogen, some dust particles so rare you could travel for years without encountering one, and the faint pressure of starlight. This interstellar space contains gas, but calling it gas seems almost misleading given its extreme tenuousness. In the space between stars, the density averages about 1 atom per cubic centimeter. For comparison, air at sea level contains about 10 to the 19th atoms per cubic centimeter. Interstellar space is less dense than air by a factor of 10 million trillion. The best vacuum we can create in laboratories on Earth, in the most sophisticated vacuum chambers, is still millions of times denser than the average density of interstellar space. Even the densest regions of interstellar space, the molecular clouds where stars form, are extraordinarily sparse by terrestrial standards. These clouds, which appear dark and opaque in photographs because they block light from stars behind them, contain perhaps 1 million atoms per cubic centimeter at their densest cores. This is dense for space, but it's still 10 trillion times less dense than air on Earth. You could travel through the densest part of a molecular cloud and not even notice. There would be no resistance to your motion, no sense of passing through anything. The emptiness extends to larger scales as well. Our Milky Way galaxy contains somewhere between 100 billion and 400 billion stars, along with vast quantities of gas, dust, and dark matter. Yet these hundreds of billions of stars occupy a disk about 100,000 light-years across and roughly 1,000 light-years thick at the Sun's location. The stars are so far apart that if you were to travel to a random location within the galaxy, you would find yourself in interstellar space, far from any star. The average distance between stars is about 5 light-years. At the scale where stars are separated by light-years, the stars themselves, objects typically about 1 million kilometers across, are essentially point-like. They occupy a negligible fraction of the galaxy's volume. Between galaxies, the emptiness reaches its most extreme. The space separating galaxies is called intergalactic space, and it's even emptier than interstellar space. The density of matter in intergalactic voids, the enormous empty regions between galaxy clusters, is approximately 1 atom per 10 cubic meters. Think about that. You could take a cube of space 10 meters on each side, large enough to contain a small house, and on average, it would contain just one single atom. This is as close to perfect vacuum as nature achieves anywhere in the universe. The scale of intergalactic distances staggers comprehension. The Andromeda Galaxy, the nearest large galaxy to our Milky Way, lies about 2.5 million light-years away. The space between our galaxy and Andromeda is largely empty, except for a few dozen small dwarf galaxies and some scattered gas clouds. Beyond our local group of galaxies, the distances grow even more immense. The Virgo cluster of galaxies, which contains thousands of galaxies, lies about 50 million light-years away. The space between galaxy clusters is measured in tens of millions to hundreds of millions of light-years, and it contains essentially nothing. So why is space so empty? The answer lies in how the universe evolved after the Big Bang. In the earliest moments, the universe was actually extremely dense. All matter and energy were compressed into a tiny volume. But the universe has been expanding ever since, and as it expands, the matter within it spreads out, becoming less and less dense. The expansion of space itself increases the distances between objects, diluting the average density of matter throughout the cosmos. Gravity works against this dilution by pulling matter together into clumps. Regions that were slightly denser than average in the early universe attracted more matter, becoming denser still, while regions that were slightly less dense lost matter to the denser regions and became emptier. Over billions of years, this process created the structure we see today. Matter concentrated into stars, which are concentrated into galaxies, which are concentrated into galaxy clusters and superclusters, with vast voids between them. But even with gravity concentrating matter into structures, the vast majority of space remains empty because the fundamental ratio of matter to space is so low. If you took all the matter in the observable universe, every atom in every star, planet, gas cloud and galaxy, and spread it uniformly throughout all of space, the density would be about 5 atoms per cubic meter. This is the average density of the universe, and it reveals that matter is extremely rare. The universe is about 5 atoms of matter per cubic meter on average, with the rest being empty space and dark energy. The emptiness of space has profound implications. It means that collisions between stars are extraordinarily rare, even in the centers of galaxies, where stars are most densely packed. When two galaxies collide, and galaxy collisions are fairly common on cosmic timescales, the stars themselves almost never hit each other. The galaxies pass through each other, like two clouds of gnats interpenetrating, without individual gnats colliding, because the distances between stars are so large compared to the stars' sizes. The emptiness also means that space travel is, in some ways, easier than it might otherwise be. A spacecraft travelling through space doesn't need to constantly dodge debris or navigate through fields of material. Space is clear. The challenges of space travel come not from crowding but from the vast distances between destinations and the energy required to cross those distances. Light from distant objects travels through this emptiness for billions of years, crossing intergalactic voids, interstellar space, and the relative crowding of planetary systems to eventually reach our telescopes. The fact that we can see distant galaxies at all, objects billions of light years away, testifies to how empty space is. If space were filled with gas or dust at densities even remotely approaching terrestrial conditions, the light would be scattered and absorbed long before travelling such distances. The emptiness of space is not a coincidence or an accident. It's a fundamental consequence of the universe's expansion, the initial density of matter after the Big Bang, and the way gravity organizes that matter into structures. The spectacular images of galaxies, nebulae, and star clusters show us the rare locations where matter has concentrated. But these are the exceptions, the islands of matter in an ocean of emptiness. The typical state of the universe is not the crowded star field or the dense nebula. It's the dark, cold, nearly perfect vacuum of intergalactic space, where a single atom might drift alone for years before encountering another, where the nearest star is so distant that its light takes millions of years to arrive, and where the overwhelming reality is not presence but absence, not matter but void, not something but nothing, extending in all directions for distances that dwarf the span of human comprehension. Why stars explode when they die? For millions or billions of years, a star exists in a state of perfect balance. Gravity pulls inward, trying to compress the star, while the heat and pressure from nuclear fusion in the core push outward, resisting that compression. This equilibrium, this careful balance between opposing forces, allows stars to shine steadily for incomprehensible stretches of time. But eventually, inevitably, the fuel runs out. For some stars, death comes quietly, a gentle fading as they shed their outer layers and cool into obscurity. But for the most massive stars, death is anything but peaceful. When these giants exhaust their nuclear fuel, they don't fade. They explode with such violence that a single dying star can briefly outshine an entire galaxy of hundreds of billions of stars. The path to a supernova explosion begins with the structure of massive stars and how they generate energy. Stars like our Sun fuse hydrogen into helium in their cores, a process that releases energy and provides the outward pressure needed to support the star against its own gravity. But massive stars, those with at least 8 times the Sun's mass, don't stop at hydrogen fusion. When the hydrogen in the core is exhausted, the core contracts and heats up until it reaches temperatures high enough to fuse helium into carbon and oxygen. This is just the beginning. For massive stars, nuclear fusion proceeds through multiple stages, each burning a different fuel. After helium burning comes carbon burning, then neon burning, then oxygen burning, and finally silicon burning. Each stage produces heavier elements as its ash, and those ashes become the fuel for the next stage. Each stage also burns faster than the previous one, because it occurs at higher temperatures and releases less energy per fusion reaction. A massive star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, but only days fusing silicon. The star develops a layered structure, like an onion, with each shell fusing a different element. The outermost layers still contain mostly hydrogen. Deeper in, a shell fuses helium. Deeper still, shells fuse carbon, neon, oxygen, and silicon in succession. At the very center lies an iron core, about 1.5 times the mass of the Sun, but compressed into a sphere roughly the size of Earth. This iron core is the end of the line. Iron occupies a special place in nuclear physics. Elements lighter than iron release energy when fused together. This is what powers stars. Elements heavier than iron release energy when split apart through fission, but iron sits at the peak of the binding energy curve. Fusing iron nuclei together doesn't release energy, it requires energy. The iron core cannot generate heat through fusion. It's an inert ball of matter, supported only by electron degeneracy pressure, the quantum mechanical resistance of electrons being compressed too closely together. The iron core grows as the silicon-burning shell above it continues converting silicon into iron. Each second, tons of iron are added to the core. The core is already incredibly dense, about 10 billion kilograms per cubic meter, and as it grows more massive, it also grows hotter and denser. The electrons supporting the core are squeezed into higher and higher energy states, reaching energies where they can do something remarkable. They can merge with protons. This process, called electron capture, or inverse beta decay, occurs when an electron is forced into a proton, creating a neutron and releasing a neutrino. The neutrino immediately escapes from the star at the speed of light, carrying energy away. This removes electrons from the core, reducing the electron degeneracy pressure that's supporting it. The core contracts further, squeezing more electrons into protons, creating more neutrons, removing more pressure support, causing further contraction. This runaway process accelerates catastrophically. Subramanian Chandrasekhar calculated in the 1930s that electron degeneracy pressure can support a maximum mass of about 1.4 solar masses, now called the Chandrasekhar limit. When the iron core exceeds this limit, electron degeneracy pressure can no longer hold it up. The core collapses. What happens next occurs in less than a second, but releases more energy than the star produced during its entire multi-million-year lifetime. The core implodes at velocities reaching 70,000 kilometers per second, nearly 1/4 the speed of light. The outer part of the core falls onto the inner part, compressing it to densities exceeding that of atomic nuclei. At these densities, around 400 trillion grams per cubic centimeter, nuclear forces become repulsive rather than attractive. The collapse halts suddenly, like a ball hitting a concrete floor. The abrupt halt of the inner core creates a shock wave that propagates outward through the infalling material. This bounce shock wave contains enough energy to blow apart the entire star, but calculations show that it stalls within milliseconds, unable to push through the still infalling outer layers. For decades, this posed a major theoretical problem. How do stars actually explode if the bounce shock stalls? The answer lies in neutrinos. During the collapse, protons and electrons combine to form neutrons, releasing vast numbers of neutrinos. The newborn neutron star at the core, incredibly hot, temperatures exceeding 100 billion degrees, produces additional neutrinos through various processes. In normal circumstances, neutrinos barely interact with matter. Trillions pass through your body every second from the sun without causing any effect. But the matter in a collapsing stellar core is so dense that even neutrinos can't escape immediately. They diffuse outward over several seconds, and during this time, a tiny fraction, less than 1% of them, interact with the infalling material. This sounds negligible, but the total neutrino energy is staggering, about 10 to the 53 ergs, roughly 100 times the energy the sun will radiate during its entire 10 billion year lifetime, released in just 10 seconds. Even if only 1% of this energy couples to the stellar material, it's more than enough to revive the stalled shockwave and drive the explosion. The outer layers of the star are blasted into space at speeds of 30,000 kilometers per second or more. This core collapse supernova, designated Type 2 if hydrogen is present in the spectrum, or Type 1b or IC if the star lost its hydrogen envelope before exploding, is the fate of all massive stars. The explosion is so energetic that it creates elements heavier than iron through rapid neutron capture. During the few seconds of the explosion, neutrons are so abundant that nuclei can capture many neutrons in quick succession, building up elements like gold, platinum, and uranium that cannot be created through normal stellar fusion. Every atom of gold in existence was created in supernova explosions or in the mergers of neutron stars. The only direct detection of supernova neutrinos occurred on February 23, 1987, when neutrino detectors on Earth registered a burst of neutrinos from supernova 1987A in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. The neutrinos arrived about 3 hours before the light became visible, exactly as predicted. The neutrinos escaped during the core collapse, while the light had to wait for the shockwave to reach the star's surface. This detection confirmed the core collapse mechanism and marked the beginning of neutrino astronomy. There's another type of supernova with a completely different mechanism, the Type 1a supernova. These occur in binary star systems, where a white dwarf, the dense remnant of a sun-like star, accretes matter from a companion star. As the white dwarf gains mass, it approaches the Chandrasekhar limit. When it crosses this threshold, carbon fusion ignites throughout the entire white dwarf, almost simultaneously, not gradually, from the center outward. The fusion releases so much energy that the white dwarf is completely disrupted. There's no neutron star remnants left behind. The entire star is blown apart. Type Ia supernovae are remarkably uniform in their energy output because they always occur at approximately the same mass, the Chandrasekhar limit. This uniformity makes them valuable as standard candles for measuring cosmic distances. Observations of distant type Ia supernova by Saul Perlmutter, Brian Schmidt, Adam Ress, and their teams in the 1990s revealed that the universe's expansion is accelerating, leading to the discovery of dark energy and earning the observers the 2011 Nobel Prize in Physics. The energy released in a supernova is distributed across different forms. About 99% goes into neutrinos, which escape into space carrying information about the core collapse. About 1% goes into kinetic energy of the ejected material, the blast wave that expands into space. Only about 0.01% goes into light, but this is still enough to make the supernova visible across billions of light years. For a few weeks, a single supernova can outshine its entire host galaxy. The remnant left behind after a core collapse supernova depends on the core's final mass. If the core is between about 1.4 and 3 solar masses, electron degeneracy pressure fails, but neutron degeneracy pressure succeeds in halting the collapse, creating a neutron star. If the core exceeds roughly 3 solar masses, even neutron degeneracy pressure cannot stop the collapse, and the core continues collapsing into a black hole. The exact threshold remains uncertain because it depends on the equation of state of nuclear matter at extreme densities, which is not precisely known. Supernova explosions enrich the interstellar medium with heavy elements. The carbon, oxygen, silicon, and iron in the ejected material mix into interstellar gas clouds, raising their metallicity, the abundance of elements heavier than hydrogen and helium. These enriched clouds eventually collapse to form new generations of stars and planets. The Sun and Earth formed from material enriched by previous supernova. Every element heavier than lithium in your body was created in a star and dispersed by a supernova or stellar wind. The shock wave from a supernova can trigger new star formation by compressing nearby molecular clouds. The expanding remnant, a shell of hot gas and energetic particles, can remain visible for thousands of years. The Crab Nebula, visible in the constellation Taurus, is the remnant of a supernova that occurred in 1054 AD and was recorded by Chinese astronomers. At its center sits a rapidly spinning neutron star, a pulsar rotating 30 times per second, powered by the rotational energy it inherited from the collapsed core. Supernova rates in galaxies depend on the star formation rate and the mass distribution of stars being formed. The Milky Way experiences roughly 2 to 3 supernovae per century on average, though we haven't witnessed a nearby visible supernova since Kepler's supernova in 1604. Most occur hidden behind dust in the galactic plane, their light obscured but their effects, shock waves, cosmic rays, heavy element enrichment, rippling through the galaxy. The most massive stars can experience even more exotic deaths. Stars exceeding roughly 130 solar masses might become pair instability supernovae, where gamma rays in the core become so energetic that they spontaneously convert into electron-positron pairs. This removes pressure support, causing catastrophic collapse and an explosion so violent that the entire star is destroyed. No remnant of any kind survives. Stars more massive still might collapse directly into black holes without exploding at all, with all their mass disappearing behind an event horizon in silence. Understanding why stars explode when they die connects nuclear physics, quantum mechanics, general relativity, and hydrodynamics. It explains the origin of elements, the formation of neutron stars and black holes, the enrichment of galaxies with heavy elements, and the triggering of new star formation. The death of massive stars through supernova explosions is not just destruction, it's creation, recycling stellar material back into space, enriched with new elements, ready to form new stars, new planets, and perhaps new life, continuing the cosmic cycle that has built the complex, element-rich universe we inhabit today, all initiated by the catastrophic collapse that occurs when fusion finally fails and gravity wins its ultimate victory over the force that gave the star life. Why one side of the moon always faces Earth. If you look at the moon on any clear night, you'll see the same familiar pattern of light and dark regions, the features we call the man in the moon or the rabbit, depending on cultural interpretation. This pattern never changes. The same side of the moon perpetually faces Earth. There is no natural rotation of the moon that would show us different faces throughout the month. Ancient astronomers noticed this peculiarity thousands of years ago, and for centuries it seemed like a remarkable coincidence. Why would the moon's rotation period exactly match its orbital period around Earth, both taking about 27 days? The answer involves no coincidence at all, but rather a physical process called tidal locking that inevitably synchronizes the rotation and orbit of any moon close enough to its planet. Tidal locking occurs because of tidal forces, the same forces that create ocean tides on Earth. Tidal forces arise because gravity weakens with distance. The side of Earth facing the moon experiences slightly stronger gravitational pull from the moon than Earth's center does, and Earth's center experiences slightly stronger pull than the side facing away from the moon. This difference in gravitational strength across Earth's diameter creates the tidal force that stretches Earth slightly, raising bulges on both the near and far sides. The same process works in reverse. Earth's gravity creates tidal bulges on the moon, though without oceans these bulges are in the solid rock itself. The moon is slightly elongated, stretched along the Earth-Moon line, with the long axis about 20 meters longer than the short axis. If the moon rotates relative to Earth, these bulges try to rotate with the moon, but Earth's gravity pulls on the bulges, trying to keep them aligned with Earth. Imagine the moon rotating slightly faster than once per orbit. As it rotates, the tidal bulge tries to rotate ahead of the Earth-Moon line, but Earth's gravity pulls more strongly on the closer bulge, creating a torque that opposes the rotation, slowing the moon down. This gravitational torque acts like friction, steadily dissipating the moon's rotational energy. The energy doesn't disappear. It converts into heat through internal friction as the moon flexes slightly, warming the lunar interior by tiny amounts. Over millions of years, this process slows the moon's rotation until it matches the orbital period. Once synchronized, the same side always faces Earth. The tidal bulges align perfectly with the Earth-Moon line, and there's no more torque trying to change the rotation. This is the state the moon reached long ago. The moon is tidally locked to Earth, rotating once on its axis in exactly the same time it takes to orbit Earth once, both periods equal to about 27.3 days. From the moon's perspective, Earth hangs nearly motionless in the lunar sky, drifting slightly back and forth due to libration, small oscillations caused by the moon's slightly elliptical orbit and tilted axis, but never rising or setting. If you stood on the near side of the moon, Earth would always be visible. If you stood on the far side, Earth would never be visible, hence why that hemisphere is sometimes mistakenly called the dark side, though it receives just as much sunlight as the near side. The timescale for tidal locking depends on several factors: Larger tidal forces lock a moon more quickly. Closer moons experience stronger tidal forces and lock faster than distant moons. Moons with more internal friction, perhaps from molten interiors, dissipate energy more efficiently and lock faster. For the moon, calculations suggest that tidal locking occurred relatively early in the moon's history, within the first 100 million years or less after its formation. By the time complex life evolved on Earth, the moon had already been showing the same face toward our planet for billions of years. Tidal locking doesn't just affect the moon, it's common throughout the solar system. Most major moons are tidally locked to their planets. Jupiter's 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, all show the same faces to Jupiter. Saturn's large moon Titan is locked. Neptune's moon Triton is locked. In fact, of all the major moons in the solar system, almost everyone is tidally locked to its planet, because they've had billions of years for tidal forces to synchronize their rotations. Some moons have been locked into more complex rotations through resonances with other moons. Mercury, though not a moon, is locked in a 3-to-2 resonance with the Sun. It rotates 3 times for every 2 orbits, a more complex tidal lock. Pluto and its large moon Charon are mutually tidally locked. Each shows the same face to the other always. Pluto rotates once per orbit, and Charon orbits once per Pluto's rotation, so they're perpetually facing each other across their orbit. The tidal locking process also affects Earth, though much more slowly because Earth is more massive than the Moon. The Moon raises tidal bulges on Earth, primarily in Earth's oceans, creating the familiar ocean tides. Earth rotates faster than the Moon orbits. A day is 24 hours, while the Moon's orbital period is about 27 days. This means Earth's rotation carries the tidal bulges ahead of the Moon's position. The bulge closer to the Moon is slightly ahead of the direct Earth-Moon line, and the Moon's gravity pulls backward on this bulge, creating a torque that slows Earth's rotation. This effect is measurable. Earth's rotation is slowing by about 2 milliseconds per century. Days are getting gradually longer as Earth loses rotational angular momentum. The angular momentum doesn't vanish, it's transferred to the Moon's orbit. As Earth slows down, the Moon speeds up slightly in its orbit, and a faster orbital speed means the Moon moves to a higher orbit. The Moon is currently receding from Earth at about 3.8 centimeters per year, precisely measured by bouncing laser beams off retroreflectors left on the lunar surface by Apollo astronauts. This process has been operating throughout Earth's history. Early in Earth's history, when the Moon was much closer, days were much shorter, perhaps only 5 or 6 hours long, and the month was shorter too. Ancient corals and other organisms that leave daily growth rings provide evidence for shorter days in the distant past. Going forward, the process will continue. In the far future, if given enough time, tens of billions of years, Earth's rotation would eventually slow to match the Moon's orbital period. At that point, Earth would be tidally locked to the Moon, just as the Moon is now locked to Earth, with the same face of Earth always facing the Moon. However, this will never happen because the Sun will evolve into a red giant in about 5 billion years, long before Earth could become tidally locked to the Moon. The expanding Sun will engulf the inner solar system, making the question of Earth's rotation academic at best. The tidal locking of the Moon has significant consequences for lunar exploration and observation. The far side of the Moon remained completely unknown until spacecraft flew around it. The Soviet Luna 3 probe in 1959 captured the first images of the far side, revealing a surface surprisingly different from the near side. The far side has many more craters and far fewer of the dark volcanic plains called Maria that dominate the near side's appearance. This asymmetry likely relates to the Moon's tidal locking. The near side experienced more volcanic activity, possibly because Earth's gravity affected the Moon's internal structure and thermal evolution. Communication with spacecraft on the lunar far side requires relay satellites because direct signals cannot reach Earth from there. China's Chang'e 4 mission, which landed on the far side in 2019, used a relay satellite positioned beyond the Moon to maintain communication. Future lunar bases on the far side would face this same communication challenge, requiring either relay satellites or cables running over the lunar surface to the near side. Tidal locking affects more than just moons. Many exoplanets discovered orbiting close to their stars are likely tidally locked, with one hemisphere permanently facing the star in daylight, while the other remains in eternal darkness. These planets, particularly those orbiting red dwarf stars, where the habitable zone is very close to the star, would have extreme temperature contrasts between their day and night sides. Understanding how atmospheres redistribute heat on tidally locked planets is crucial for assessing their potential habitability. The fact that one side of the Moon always faces Earth is not a lucky accident, but the inevitable result of physical forces operating over immense timescales. Every moon close enough to its planet will eventually lock, synchronizing its rotation to its orbit. The Moon reached this state billions of years ago, and it will remain locked for the remaining lifetime of the Earth-Moon system. The same face that witnessed Earth's formation, the rise of life, the age of dinosaurs, and the emergence of humanity will continue watching Earth for billions of years to come, held in place not by chance but by the patient, inexorable work of tidal forces that have shaped orbital dynamics since the solar system formed, creating the familiar face we see in the night sky every month, unchanging and eternal from our human perspective, yet itself the product of changes stretching across geological deep time. Why some asteroids are made of metal? Most asteroids are dark, rocky bodies composed of silicate minerals similar to the rocks found on Earth's surface. But among the hundreds of thousands of asteroids orbiting in the main belt between Mars and Jupiter, a small population stands out as fundamentally different. These are the metallic asteroids, composed primarily of iron and nickel rather than rock. They gleam brightly in reflected sunlight, their surfaces shining with the luster of exposed metal. The most famous of these is Psyche, a massive asteroid about 226 kilometers in diameter that appears to be almost entirely metallic. Understanding why some asteroids are made of metal means understanding the violent history of the early solar system and the process by which planets form their layered structures of core, mantle, and crust. The story of metallic asteroids begins with planetary differentiation, the process by which a planetary body separates into layers based on density. When a planet or large asteroid forms, it starts as a mixture of materials, rock-forming elements like silicon, oxygen, magnesium, and calcium mixed with metallic elements like iron and nickel. If the body grows large enough and contains enough radioactive elements, it heats up from the decay of radioactive isotopes and from the energy of continued impacts as it accretes more material. When the temperature rises above the melting point of iron, about 1538 degrees Celsius, something dramatic happens. The iron, being denser than the surrounding silicate rock, begins to sink toward the center of the body. This process, called the iron catastrophe, releases enormous amounts of gravitational potential energy as the dense metal falls inward, further heating the body. The result is a differentiated structure with a dense iron-nickel core at the center, surrounded by a rocky mantle of lighter silicate minerals, and potentially a thin crust at the surface. This is the same basic structure that Earth possesses, an iron-nickel core containing about 32% of Earth's mass, surrounded by a silicate mantle and crust. Planetary differentiation occurred in the early solar system in bodies large enough to melt their interiors. Earth differentiated, Mars differentiated, Venus almost certainly differentiated. Even some large asteroids, like Vesta, which has a diameter of about 525 kilometers, underwent differentiation. Vesta has a basaltic crust formed from volcanic activity, indicating that it once had a molten interior with a metallic core. The asteroid Ceres, the largest object in the asteroid belt, at about 940 kilometers in diameter, shows evidence of differentiation as well. Once a body has differentiated into core, mantle, and crust, it becomes vulnerable to catastrophic disruption. The early solar system was a chaotic place, filled with planetesimals, asteroid-sized objects, colliding frequently as they orbited the young sun. Computer simulations of this period show that collisions were not just common, but inevitable. Some collisions led to accretion, with two bodies merging to form a larger one, but others were catastrophically disruptive, shattering one or both bodies into fragments. When a differentiated planetesimal is shattered by a sufficiently energetic collision, the fragments don't all have the same composition. Pieces from the core are metallic, pieces from the mantle are rocky, pieces from the crust might be volcanic basalts if the body had volcanism. These fragments become separate asteroids, each one representing a sample of a specific layer from the parent body. This is why we find three distinct types of asteroids in the main belt: C-type asteroids, which are carbonaceous and primitive, never having melted; S-type asteroids, which are stony and represent crustal and mantle material; and M-type asteroids, which are metallic and represent exposed cores. The M-type designation comes from their metallic composition, though determining composition from Earth requires spectroscopic analysis and radar observations. M-type asteroids are typically much more reflective than rocky asteroids. Their albedo, or reflectivity, ranges from about 10 to 18%, compared to 3 to 7% for dark carbonaceous asteroids. This high reflectivity occurs because metal reflects light efficiently compared to dark silicate minerals. The spectroscopic signatures of M-type asteroids show features consistent with iron and nickel, though definitively confirming their composition requires spacecraft missions or detailed radar studies. Radar observations provide particularly strong evidence for the metallic nature of M-type asteroids. Radio waves reflect differently from metal surfaces than from rocky surfaces. Metal is a much better radar reflector, and radar polarization measurements can distinguish metallic from rocky compositions. Studies using the Arecibo Observatory and Goldstone Solar System radar have confirmed that many M-type asteroids have radar properties consistent with metallic surfaces, supporting the interpretation that they're exposed planetary cores. The asteroid Psyche represents the most studied example of a metallic asteroid and the target of NASA's Psyche mission, launched in 2023 and scheduled to arrive at the asteroid in 2029. Psyche is unusual even among M-type asteroids because of its enormous size and apparently high metal content. If Psyche is indeed the exposed core of a differentiated planetesimal, it would be the only core of a planetary body that humans have ever been able to study directly. Earth's core lies 2,900 kilometers beneath the surface, completely inaccessible. Mars's core is similarly hidden, but Psyche's core is exposed, available for investigation. The composition of metallic asteroids reflects the composition of planetary cores more generally. Iron and nickel are the dominant elements, present in roughly the same proportions found in iron meteorites that fall to Earth, about 90% iron and 10% nickel, though with some variation. These proportions match what cosmochemical models predict for the cores of terrestrial planets. Additional elements found in smaller quantities include cobalt, phosphorus, sulfur, and carbon. Some models suggest that planetary cores might contain significant amounts of lighter elements, like silicon or oxygen, dissolved in the molten metal, but whether these would be retained in a fragmented, solidified core like Psyche remains uncertain. The value of metallic asteroids extends beyond scientific interest. These asteroids contain enormous quantities of valuable metals. A single metallic asteroid a kilometre across might contain more platinum group metals than have ever been mined on Earth. The asteroid 16 Psyche, if it's as metallic as estimates suggest, would contain iron alone worth quadrillions of dollars at current prices. Though of course, actually mining and returning such quantities would crash commodity markets and is far beyond current technological capabilities. Nevertheless, the concept of asteroid mining has captured imaginations and may become economically viable in the future as space access costs decrease and in-space manufacturing develops. Not all M-type asteroids are metallic, which complicates the picture. Some asteroids classified as M-type, based on their reflectivity and spectroscopic properties, might actually be enstatite chondrites, a rare type of rocky meteorites with high reflectivity, or other unusual rock types that mimic the appearance of metal. This demonstrates the difficulty of determining asteroid composition remotely. Only with spacecraft missions, sample return, or eventually human exploration can we definitively establish what these objects are made of. The formation of metallic asteroids also constrains the timing and locations of planet formation in the early solar system. Differentiation requires heating, which comes primarily from radioactive decay of short-lived isotopes like aluminum-26, which has a half-life of only 717,000 years. For aluminum-26 to provide significant heating, the planetesimal must form within a few million years of the solar system's birth, while aluminum-26 is still abundant. This timing constraint suggests that the parent bodies of metallic asteroids formed quickly within the first few million years of solar system history. The subsequent disruption of these differentiated bodies likely occurred during a period of intense bombardment, possibly associated with dynamical instabilities in the giant planet's orbits. The Nice model, named after the city in France where it was developed, proposes that Jupiter, Saturn, Uranus, and Neptune formed in a more compact configuration and later migrated to their current orbits. This migration scattered planetesimals throughout the solar system, dramatically increasing collision rates and leading to the disruption of many differentiated bodies. The timing of this instability, estimated at around 600 to 800 million years after the solar system formed, would have been late enough for the large planetesimals to have already cooled and solidified after their differentiation. Iron meteorites that fall to Earth are fragments of metallic asteroids, providing samples we can study in laboratories. These meteorites show distinctive crystalline structures called Widmanstätten patterns, interlocking crystals of two different iron-nickel alloys, camosite and taenite, that form only when molten metal cools extremely slowly over millions of years. The size and structure of these crystals reveal the cooling history of the parent body's core. Some iron meteorites cooled at rates of only a few degrees Celsius per million years, consistent with cooling in the interior of a body tens to hundreds of kilometers in diameter, exactly the size of the differentiated planetesimals that became the parent bodies of metallic asteroids. The Widmanstätten patterns become visible when iron meteorites are cut, polished and etched with acid. The two iron-nickel alloys etch at different rates, revealing the crystalline structure. These patterns are beautiful and distinctive, and they can only form under the pressure and temperature conditions found deep within planetary cores, providing strong evidence that iron meteorites, and by extension metallic asteroids, genuinely represent fragments of ancient planetary cores. The distribution of metallic asteroids in the asteroid belt provides additional clues about the formation and evolution of the solar system. M-type asteroids are found throughout the main belt, but are somewhat more common in the middle regions. This distribution might reflect where conditions were favourable for forming large, differentiated planetesimals and where subsequent collisions occurred that could disrupt them. The relative scarcity of metallic asteroids compared to rocky ones, M-types represent only about 5 to 10% of asteroids. Makes sense given that a differentiated body's core contains much less volume than its mantle and crust combined. Some metallic asteroids might not be fragments of differentiated bodies at all, but could have formed through different processes. Certain types of impactors, if they struck at very high velocities, could strip away a body's mantle and crust while leaving the core relatively intact. Alternatively, some metal-rich asteroids might have formed from material that was already enriched in metals during the solar system's formation, though this seems less likely given what we know about how materials were distributed in the protoplanetary disk. The Psyche mission will answer many questions about metallic asteroids when it arrives at its target. The spacecraft will map Psyche's surface in detail, measure its gravity field to determine how mass is distributed internally, study its magnetic properties to search for evidence of an ancient magnetic field that might have existed when the core was still molten, and analyze its composition using spectrometers and cameras. These measurements will reveal whether Psyche is indeed a nearly pure metallic core, as many scientists suspect, or whether it has a more complex structure with rock mixed in or covering parts of the surface. Understanding metallic asteroids means understanding planetary cores, the process of differentiation, the violence of the early solar system, and the building blocks from which planets formed. Every metallic asteroid is a window into planetary interiors, exposing material that would otherwise remain forever hidden beneath thousands of kilometers of rock. These fragments of ancient cores, forged in the heat of differentiation and revealed by catastrophic collisions, represent some of the oldest processed materials in the solar system. Samples of the massive bodies that either grew into planets or were destroyed in the chaos of planetary formation, leaving behind their metallic hearts orbiting the Sun as testament to the violent processes that shaped our cosmic neighborhood billions of years ago. Why silicon-based life forms might be possible. For as long as scientists have contemplated life beyond Earth, one element has persistently captured imaginations as a possible alternative to carbon: silicon. Science fiction has explored silicon-based aliens in countless stories, from rock-like creatures that metabolize minerals to crystalline beings that think at geological timescales. But these fictions rest on a foundation of genuine chemistry. Silicon sits directly below carbon in the periodic table, shares many of carbon's most important properties, and is far more abundant in Earth's crust than carbon. Yet despite this abundance and chemical similarity, silicon never became the basis for life on Earth. Understanding why silicon-based life might still be possible elsewhere requires examining both the remarkable parallels between silicon and carbon chemistry and the significant obstacles that would need to be overcome. Carbon's dominance in biochemistry stems from several key properties. Carbon atoms can form 4 strong covalent bonds with other atoms, allowing them to link together into chains, branches, and rings of almost unlimited complexity. A single carbon atom might bond to 4 other carbon atoms, creating a 3-dimensional network. Or carbon atoms might link into chains hundreds or thousands of atoms long, with various other elements, hydrogen, oxygen, nitrogen, phosphorus, sulfur, attached at different positions. This versatility allows carbon to form millions of different molecules, from simple methane with 1 carbon atom to DNA molecules containing billions of carbon atoms arranged in precise sequences that store genetic information. Silicon shares carbon's ability to form 4 covalent bonds. The electron configuration that gives carbon its bonding properties is mirrored in silicon, making silicon capable of forming similar structures: silicon chains, silicon rings, silicon networks. In fact, silicon chemistry forms the basis of an entire class of synthetic materials called silicones, which consist of chains of alternating silicon and oxygen atoms with organic groups attached. These materials, familiar as sealants, lubricants, and medical implants, demonstrate that silicon can indeed form large complex molecules. But silicones are human inventions, created in laboratories and factories. Nature has not produced silicon-based organisms, at least not on Earth, despite silicon being about 900 times more abundant in Earth's crust than carbon. The primary obstacle to silicon-based life under Earth-like conditions is silicon's relationship with oxygen. When carbon reacts with oxygen, when it burns, it forms carbon dioxide, a gas at normal Earth temperatures. This gas can be easily expelled from an organism and recycled back into the environment. Plants take in carbon dioxide and use it to build sugars through photosynthesis. Animals exhale carbon dioxide as a waste product of metabolism. Carbon dioxide dissolves readily in water, allowing it to be transported in blood and participate in various chemical reactions. The carbon cycle that sustains Earth's biosphere depends on carbon dioxide being gaseous, mobile, and chemically accessible. Silicon's equivalent compound is silicon dioxide, silica, quartz, sand, rock. When silicon burns with oxygen, it forms a solid. This solid is extremely stable, nearly insoluble in water, and chemically unreactive under normal conditions. An organism that metabolizes silicon and oxygen the way Earth organisms metabolize carbon and oxygen would accumulate solid mineral waste inside its body or would need to excrete sand. The waste products of silicon metabolism cannot easily be transported in fluids, cannot be exhaled as gas, and cannot be recycled through environmental cycles the way carbon dioxide can. This fundamental difference makes silicon-oxygen chemistry poorly suited for biochemistry on worlds with oxygen-rich atmospheres and liquid water. However, removing oxygen from the equation changes the possibilities dramatically. In environments where oxygen is absent or rare, silicon chemistry behaves very differently. Silicon forms stable bonds with hydrogen, creating silanes, molecules analogous to hydrocarbons, but with silicon replacing carbon. The simplest silane is silane itself, with one silicon atom bonded to 4 hydrogen atoms, analogous to methane. Longer chains are possible, disilane with 2 silicon atoms, trisilane with 3, and so on. These silicon-hydrogen chains are reactive and unstable compared to carbon-hydrogen chains, but in the absence of oxygen, they might persist long enough to serve biological functions. Temperature plays a crucial role in silicon chemistry. At Earth's surface temperatures, silicon-silicon bonds are relatively weak compared to carbon-carbon bonds. Silicon compounds tend to break apart more easily, making long, stable silicon chains difficult to maintain. But at much colder temperatures, the kinds found in the outer solar system, silicon chemistry becomes more favorable. Chemical reaction rates slow down dramatically at low temperatures, which could actually help stabilize silicon compounds that would rapidly decompose at room temperature. Meanwhile, some of the alternative solvents that might replace water at these temperatures could interact with silicon compounds in ways that favor complex chemistry. Liquid methane and ethane, which exist naturally on Saturn's moon Titan at temperatures around -180 degrees Celsius, represent one possibility. In these hydrocarbon seas, water is as hard as rock and oxygen is locked away in ice and minerals. Silicon compounds might dissolve in liquid hydrocarbons more readily than in water, and without oxygen to react with, silicon could potentially form the complex, diverse molecules that life requires. The chemistry would be radically different from Earth's biochemistry. Reaction rates would be thousands of times slower, molecules would have different shapes and properties, and the fundamental mechanisms of energy storage and information transfer would need to be reimagined. But the basic requirements for life, complex molecules that can store information, catalyze reactions, and self-replicate, might still be achievable with silicon as the central element. Liquid nitrogen, which exists at even colder temperatures, offers another potential solvent. Nitrogen becomes liquid at -196 degrees Celsius at Earth atmospheric pressure. A world with lakes or oceans of liquid nitrogen would be incomprehensibly cold by Earth standards, but chemical reactions would still occur, just very slowly. Silicon compounds might be more stable and diverse at these extreme temperatures, allowing them to form the kinds of complex structures that life needs. Another approach to silicon-based life involves thinking beyond complete replacement of carbon. Instead of imagining organisms built entirely from silicon, consider hybrid biochemistries that use both elements. Silicon might form structural components, while carbon handles information storage and catalysis. Silicon-oxygen minerals could serve as skeletal elements, providing rigid support structures that carbon-based soft tissues attach to. This is essentially what Earth organisms do. Bones, shells, and the glass-like structures of diatoms all incorporate silicon compounds, though the fundamental biochemistry remains carbon-based. A true silicon-based organism would integrate silicon more deeply into its biochemistry, perhaps using silicon-containing molecules for energy storage, membrane structure, or even genetic material. The information storage challenge represents one of the most significant hurdles for silicon-based life. DNA and RNA work remarkably well as information storage molecules because they're stable enough to preserve information over time, but flexible enough to be copied and modified. The sugar-phosphate backbone provides structural support, while the nitrogen bases store actual information through their sequence. Could silicon replace the carbon in the sugar molecules? Silicon-containing analogues of sugars and nucleotides have been synthesized in laboratories, demonstrating that such molecules can exist. Whether they could reliably store and transmit information across generations in a living organism remains unknown, but the chemistry doesn't appear to forbid it outright. Energy metabolism in silicon-based organisms presents another puzzle. Earth organisms primarily extract energy by rearranging chemical bonds, breaking bonds in food molecules, and forming new bonds in waste products, capturing the released energy in the chemical bonds of ATP. Silicon-based organisms would need analogous processes. Perhaps they could oxidize silanese to release energy, though the solid silicon dioxide waste product would be problematic. Or they might use entirely different metabolic pathways based on silicon's interaction with halogens like fluorine or chlorine, creating different waste products that could be more easily managed. In extremely cold environments, metabolic rates could be extraordinarily slow. A silicon-based organism might take years to grow or reproduce, operating on timescales that would make watching grass grow seem rapid by comparison. The evolution of silicon-based life would require a planet with very specific conditions. Silicon would need to be available in reactive forms rather than locked into stable minerals. The temperature would probably need to be very cold to favor silicon chemistry over its tendency to decompose. Oxygen would need to be absent or rare to prevent silicon from forming insoluble silicon dioxide. A suitable solvent other than water would need to exist: liquid hydrocarbons, liquid ammonia, or something even more exotic. These conditions might exist on certain moons in the outer solar system, on rogue planets drifting through interstellar space, or on exoplanets orbiting dim red dwarf stars, where temperatures never rise above the freezing point of water. Titan, with its lakes of liquid methane and ethane, its thick nitrogen atmosphere, and its extremely cold temperatures, represents perhaps the best candidate in our solar system for silicon-based life. NASA's Dragonfly mission, scheduled to launch in the late 2020s, will explore Titan's surface and could potentially detect signs of exotic biochemistry if it exists. The mission won't specifically look for silicon-based life. Nobody knows exactly what signatures such life would produce, but it will analyze organic chemistry in Titan's lakes and atmosphere, searching for patterns that might indicate biological processes. Even if silicon-based life exists nowhere in the universe, studying the possibility expands our understanding of chemistry's relationship to biology. It forces us to question our assumptions about what life requires and what forms it might take. Every element brings different properties, different strengths and weaknesses, different possibilities and constraints. Carbon happened to be the element that worked on Earth under Earth's conditions, but Earth represents just one set of conditions among countless possibilities across the universe. The theoretical possibility of silicon-based life also highlights a challenge in searching for extraterrestrial life. Most of our detection methods assume life will be similar to Earth's, producing oxygen, methane, or other gases we associate with biological activity, building structures we would recognize, using chemistry we understand. But silicon-based life operating in liquid methane seas at -180 degrees Celsius would produce completely different signatures. It might metabolize compounds we consider inert waste products and excrete substances we consider essential for life. Its waste products might be our nutrients, and vice versa. We might look directly at a world covered in silicon-based organisms and not recognize it as inhabited because we're searching for carbon signatures. Silicon-based life might be possible in environments so different from Earth that the very definition of life becomes strained. Perhaps silicon-based entities would be better described as self-organizing chemical systems rather than organisms in any sense we would recognize. They might grow and reproduce on timescales of centuries. Their metabolism so slow that a single thought, if they think at all, might take years to form. They might not have discrete bodies with clear boundaries between self and environment, but instead exist as diffuse networks of silicon-based chemistry spread across vast areas. They might not die in any meaningful sense, but simply cease maintaining organization and gradually disperse back into their environment. Why silicon-based life forms might be possible comes down to chemistry being flexible, creative, and opportunistic. The laws of chemistry operate everywhere in the universe, but they produce different outcomes under different conditions. Silicon's chemical properties give it potential as a basis for complex, self-organizing systems under the right circumstances. Circumstances that apparently don't exist on Earth, but might exist elsewhere. From the hydrocarbon lakes of Titan to hypothetical ice worlds, orbiting dim stars to environments we haven't yet imagined, silicon might be constructing molecules, storing information, and powering metabolisms in ways that parallel carbon-based life, just enough to recognize as living while remaining alien enough to challenge everything we thought we knew about biology, proving that life's possibilities extend beyond the single example we know to encompass chemistries as diverse as the cosmos itself. Why space looks black. When astronauts look out the windows of the International Space Station, they see a view that never fails to inspire awe. Earth below with its blue oceans and swirling white clouds, and beyond it, the blackness of space dotted with brilliant points of starlight. That darkness seems natural and expected. Space is far from the sun, far from Earth's atmosphere, so of course it's dark. But this simple explanation masks a puzzle that perplexed astronomers for centuries. If the universe is infinite and filled with stars in every direction, then no matter where you look, your line of sight should eventually hit a star. The entire sky should blaze with light, as bright as the surface of the sun in every direction. Yet space is dark. This contradiction, known as Olbers' paradox after the German astronomer who popularized it in the 19th century, reveals deep truths about the universe's nature, age, and evolution. The puzzle seemed straightforward to early astronomers. Imagine the universe extends forever in all directions, filled uniformly with stars. Draw an imaginary sphere around Earth at any distance. That sphere contains a certain number of stars. Now draw a larger sphere at twice the distance. This larger sphere has 4 times the surface area, so it contains 4 times as many stars. Each individual star appears fainter because it's farther away. Brightness decreases with the square of distance, but there are 4 times as many stars, exactly compensating for their individual faintness. Every shell at every distance contributes the same amount of light. If the universe is infinite, there are infinitely many such shells, so the total light should be infinite. The night sky should be blindingly bright. Clearly, this doesn't match what we observe. The night sky is dark except for individual stars, planets, and the faint band of the Milky Way. Something must be wrong with the reasoning. Early astronomers proposed various solutions. Perhaps dust between stars absorbs starlight, darkening distant regions. But this doesn't really solve the problem. The dust would heat up from absorbed starlight and would eventually glow just as brightly as the stars themselves. Perhaps stars aren't distributed uniformly, with empty voids creating dark patches. But if the universe is infinite and eternal, stars should exist everywhere eventually, filling in any voids given enough time. The true solution involves the universe's finite age and its expansion, concepts unknown when Olbers formulated his paradox. The universe is not infinitely old. It began roughly 14 billion years ago in the Big Bang. Light travels at a finite speed, so we can only see light from objects whose light has had time to reach us since the universe began. The observable universe has a boundary, not a physical edge, but a horizon beyond which we cannot see, because light from more distant regions hasn't had enough time to reach us yet. This finite light travel time alone would solve Olbers' paradox, even if the universe weren't expanding. There simply aren't infinitely many stars visible. Only those within about 14 billion light-years, the distance light can travel in the age of the universe. This limits the total amount of starlight reaching us to a finite value, much less than would be needed to make the sky bright everywhere. But the universe's expansion adds another crucial element. Distant galaxies are receding from us as space itself expands. This recession causes their light to be redshifted, stretched to longer wavelengths. Light that left a distant galaxy as visible or ultraviolet radiation arrives, at Earth shifted into infrared or even microwave wavelengths. Our eyes cannot detect infrared or microwave light, so this redshifted radiation doesn't contribute to the visible brightness of the sky. The farther away a galaxy is, the faster it's receding, and the more severely its light is redshifted. The most distant galaxies we can observe have their visible light redshifted so far that it arrives as infrared or even radio waves. The cosmic microwave background radiation demonstrates this effect perfectly. This radiation, released when the universe was only about 380,000 years old, fills all of space uniformly. When it was emitted, it was visible an infrared light with a temperature of about 3,000 degrees. But in the billions of years since then, the universe has expanded by a factor of about 1,100. The wavelengths of this radiation have been stretched by the same factor, shifting what was once visible light into microwave wavelengths. The temperature corresponding to this radiation has dropped to less than 3 degrees above absolute zero. If we had eyes that could see microwaves, the sky would glow uniformly in every direction with this faint microwave light. But in visible light, it contributes nothing, leaving the sky dark. Another factor contributing to the darkness of space is the finite lifespan of stars and galaxies in their current bright state. Stars don't shine forever. They exhaust their fuel and fade. The universe's star formation rate was higher in the past and is declining now as gas is used up. In the far future, the universe will contain many more dead stellar remnants than active shining stars. Even if the universe were infinitely old, which it isn't, the sky might still be dark because most stars would have long since burned out. The darkness also depends on perspective. From Earth's surface, the atmosphere scatters sunlight, making the daytime sky bright blue, and the nighttime sky somewhat illuminated by air glow and scattered artificial light. In space, without atmosphere to scatter light, the sky appears black in all directions, except where you're looking directly at a light source. Sunlight doesn't fill space with general brightness the way it illuminates Earth's atmosphere. Light travels in straight lines, and unless it's scattered or reflected by something, it remains invisible. You can be in bright sunlight in space, with the sun illuminating your spacecraft, but when you look away from the sun, you see only darkness and stars. The blackness of space also reveals something about the nature of light and vision. We see objects because they emit or reflect light into our eyes. Empty space contains no particles to scatter or reflect light, so there's nothing to see. It appears black. This is different from looking into a dark room on Earth, where at least some scattered light usually reveals dim shapes. Space between stars is truly empty of matter, with typically less than 1 atom per cubic centimetre. With so few particles to interact with light, the light simply passes through unaffected, leaving space black. Interstellar dust does exist, and it does affect starlight, but not enough to solve Olber's paradox. The dust absorbs and scatters light from stars behind it, causing extinction, making those stars appear fainter or invisible. This creates the dark dust lanes visible in photographs of the Milky Way and other galaxies. But the dust also glows faintly in infrared light from absorbed stellar radiation. The net effect is to redistribute light from visible to infrared wavelengths, not to eliminate it entirely. Even in regions with many visible stars, the spaces between them remain black. The Orion Nebula, one of the brightest nebulae visible to the naked eye, appears as a glowing cloud because gas in the nebula fluoresces in response to ultraviolet light from young hot stars within it. The gas absorbs ultraviolet light and re-emits it as visible light, making the nebula glow. But between the glowing gas clouds, space remains dark. Only where matter exists to interact with light does the light become visible. From certain perspectives, space isn't quite black. Sensitive instruments can detect faint glows from various sources. Zodiacal light, caused by sunlight reflecting off dust particles in the inner solar system, creates a faint glow along the ecliptic. Airglow from Earth's upper atmosphere creates a faint luminescence visible from orbit. The integrated starlight from billions of faint, unresolved stars creates a faint background glow called the extragalactic background light. But these glows are extraordinarily faint, thousands of times dimmer than the darkest sky visible from Earth's surface, and our eyes cannot detect them. To human vision, space appears black. The darkness of space has practical implications for astronomy. Because space is black, stars and other objects stand out clearly against the background without competing light washing them out. The best ground-based telescopes are built on remote mountaintops, far from city lights, precisely to take advantage of darker skies. But even the darkest Earth-based site cannot match the blackness of space, where no atmosphere scatters light and where the sky is dark even in the direction of the sun. This darkness also affects spacecraft and astronaut safety. On the shadowed side of Earth or another planet, or in the shadow of the spacecraft itself, darkness is absolute, except for starlight. Astronauts working in shadow must use artificial lights because the starlight alone is far too faint to see by. The contrast between brilliant sunlight and deep shadow is extreme, creating challenges for cameras and human eyes trying to see details in both bright and dark areas simultaneously. The question of why space looks black connects to the deepest questions about the universe's structure and history. Space is dark because the universe had a beginning, because it's expanding, because light travels at a finite speed, and because stars have finite lifetimes. If any of these factors were different, if the universe were infinitely old and static, for instance, the sky would not be dark. The darkness itself is evidence for the Big Bang, for cosmic expansion, for the finite age of the universe. Every time you look up at the night sky and see darkness punctuated by stars rather than a uniform blaze of light. You're seeing direct evidence that the universe had a beginning, that it's been expanding for billions of years, stretching the light from distant sources into wavelengths your eyes cannot detect, leaving the spaces between stars as dark voids that reveal the fundamental nature of the cosmos through their very emptiness.